Thanks for coming. My name is Dimitri Stiliadis. I'm actually working with Stefano Stabellini. Some of you might know Stefano. He's the guy that did most of this work. But unfortunately, Stefano is caught in some immigration red tape, and he couldn't join us in Toronto, so he's stuck back and he's waiting for feedback. He has actually scheduled also some conference call, I think, for next week. He has invited anybody interested for details or a deep technical discussion to follow up on that. So what am I going to talk about this today? And the title of the talk is Paravirtualization for socket calls. It is a little, actually, it has some more general implications. And first of all, I want to explain why we are doing what we are doing, right? It's a little bit different than what is out there. And we actually have, there is a reason behind this insanity. So I'm going to try to explain the motivation of why we are doing it and some use cases. I'm going to explain a little bit about the protocol that we are using in order to implement it, talk a little bit about performance, and if we have time, I'll show you some quick demo of the whole work here. So what we started actually to do, and starting on why we're working on this, is we looked at the way that security is implemented within containers and Docker and this type of environments. And we quickly realized that, and that's something well known actually, lots of people talk about it in the community. There are a lot of questions about how secure can a Docker environment be? Can we make it multi-tenant? Can it apply in a generic case? So if we look a little bit at the, and I know I'm at the Zen Developer Summit and I'm talking about Docker, but there is a reason for this discussion, because I'm trying to motivate what we are trying to do here. And if we look at the security of a container environment, right, how can we contain a container environment? There are a lot of capabilities within the Linux subsystems in order to try to minimize the attack surface, right? So there is capabilities, there is Secom, there is SC Linux, there is AppArmor. All these are the tools we have in order to contain the applications. And the container community has done an excellent job on creating the defaults for a lot of those. However, the defaults can be always bypassed, and they can be bypassed by applications that are trying to do something, and we'll see some examples of that. There is the security of the container images themselves. People pull the images out of the Docker Hub or whatever, and there is a whole set of tools to do vulnerability analysis for all these things. There is access control and the security of the daemon, of the Docker daemon, or whatever is the container management daemon, and there is a whole bunch of access control mechanisms there. There is networking and communications, and there are several options there. And then there is the kernel itself. In the end of the day, when we deploy containers, the attack surface of the kernel remains the POSIX interface, right? It remains the whole system call interface that somebody can attack the kernel. So there is a lot of work there, and there is recommendations upon recommendations on how to configure a system to actually make it secure within a container environment. And very often, one of the recommendations is actually run containers in VMs, right? Because we cannot really isolate fully the kernel because of the POSIX interface or all the other dependencies. The recommendation at the end of the case comes, well, use hardware virtualization to partition containers, run containers from a specific user in one VM, and create multiple VMs for users. But in reality, this looks like that, right? It's like hundreds and hundreds of switches that somebody is going to get wrong. And if they get it wrong, then they are essentially opening up their system for attacks. And the obvious attacks that can happen is, well, I go and put all kinds of facilities for Secomp and PPF and NetFilter, whatever. I use all the capabilities of the kernel. But if an application manages to escape into the kernel, then game is over, and it can escape and destroy all the other applications. And in reality, the kernel is not free of bugs, right? There are several bugs reported every year with respect to the kernel. And actually, Stefano did some comparison that there was, I think, 4 critical vulnerabilities on Zen versus like tens of vulnerabilities on the kernel over the last couple of years, right? So the attack surface of a hypervisor, usually, in most cases, it ends up being much smaller than the attack surface of the Linux kernel because it exposes much less capabilities. So for this reason, as I said, a lot of people are saying when we are deploying containers in production, let's deploy the containers inside virtual machines. And if you see what it means, this is we end up with an architecture like this on the left, where we have essentially virtualization and we have the containers inside the virtual machines, as opposed to the standard Docker model that essentially runs no hypervisor, and in reality it can run with much less overhead. And what is the overhead here, right? So the overhead here is in reality when we are running, one of the big reasons that people embraced containers, right, is the simplicity and how lightweight they are, right? I don't need to go through a lot of hoops in order to deploy containers, and potentially my performance is not affected. I get native Linux kernel performance without the overhead of the hypervisors, and in most cases, these overheads are I/O, right? If you think about it, it's not like on the execution of instructions, if I run a strictly CPU-bound workload, in most cases, the overheads are on I/O. And when we see on the I/O case, essentially what is happening is the hypervisor creates a physical machine abstraction, right? The hypervisor lies to the guest operating system and prevents its virtual devices. And this means that I'm going through several steps of translations, if you want here, between what the application wants to do and several devices here. What do I mean by that? If we take a standard, for example, network implementation, we essentially have the TCP/IP stack of the guest together with a bridge, because the containers will need a bridge potentially or some form of networking capability inside the guest to talk to each other in order to go to a virtual device, to come up on the other side of the virtual device. And then because we have multi-tenancy there, we'll go through again an IP stack and another bridge. And in order to solve all the networking problems we have here, we're going to do several forms of NAT translations. That's what Docker chooses to do. Or potentially we're going to use tunnels and put Open vSwitch in the picture. And do a whole bunch of stuff. So in order to deploy something like that, we end up with a lot of complexity. We end up with a lot of complexity both operationally and from an operation standpoint. So what we thought we need is, ideally, we want the container performance and simplicity with a virtual machine isolation. And we try to figure out what is this right balance between the simplicity of the containers and the virtual machine isolation. And then we thought, we need to change the assumptions here. And there is a very fundamental assumption on anything that we do in virtualization, is that the host OS and the guest OS can be different, right? So I can run any guest OS on top of the host, on top of the hypervisor, and they can use completely different operating systems, and I need to support multiple operating systems on top of the hypervisor. That is a fundamental assumption. That's why virtualization was born, right? Now, what if we remove this assumption? What if we actually say that the hypervisor, or DOM0 in the case of Zen, is the exact same type of kernel and the exact same type of OS as the guests? What if we make these simplified assumptions and then we realize that the place where we need to abstract, the place where we need to do the abstraction, is not necessarily the device, is not the hardware, but we can actually do the abstraction at a higher level and have many more semantics. And by doing the abstraction at a higher level, we can actually simplify some things and potentially make some other things more complex, but that's why we are discussing this whole idea. So the approach we said is, what if we create an idea here where we have the hypervisor essentially virtualize, right? Virtualize guests essentially, but the guests pretty much are operating as a system call proxy. So essentially, when a container, when an application does a system call, the guest will implement some of the system calls internally on the guest when this is needed, and they are mandatory for the guest operation. And we can see some of these system calls, for example, all the namespace system calls, the answer system call, and so on, can be restricted within the guest, so a container cannot escape anywhere other than the guest operating system. And for the system calls that we really want something else, that we want I/O functions, essentially, we want file access, network access, the very important system calls, or potentially the real time, because every hypervisor seems to be having a problem with real time. So for the system calls that we want essentially hardware support, we want some I/O function, then we proxy the system calls down to the hypervisor or the root kernel or whatever is sitting underneath. And then what we get by that is that we get two things. First of all, we minimize the attack surface of the underlying operating system, right? The hypervisor, essentially, we minimize the attack surface on a very small number of hypercalls that are happening between the guest and the hypervisor. So we have this benefit immediately of reduced attack surface. We have some other benefits. The other benefit in security is a little bit security by obscurity, but by translating a system call to a hypercall and then back to a system call, the several levels of translation have the potential of helping us catch a potential bug. Because if one of the levels has a bug, for example, if there is a buffer overflow on the system call that the kernel has, and then the application is trying to exploit that, there is a good chance that the guy in the middle during this translation is going to catch the bug. Now, this is not science, right? But it has been used in some production systems by some very big companies, as I understand, as a way of minimizing the attack surface a little bit by obfuscating these calls, right? By creating these several translations of calls. So how would that work in a Zen environment? In a Zen environment, it's pretty much a simple architecture that we chose to implement. We use the standard front-end, back-end driver implementation to essentially allow the majority of the system calls to be processed by the guest kernel, and very specific system calls, they are essentially proxied directly to the backend, and they are implemented directly in DOM-U. And what do we mean by that, and I will explain that in a little bit more detail, is that when, for example, I do a socket call, and that's the first implementation we did, when I open a socket on the guest, the socket is not actually open on the guest, the socket is actually open directly on DOM0. So essentially, you are getting network resources directly out of DOM0 without the guest understanding that this is actually happening. In reality, this type of abstraction or virtualization would mean that two guests can talk to each other over 127.0.0.1. They have both of them, they have opened a port on DOM0 without any network translations, without any devices. And there is a reason that we actually, chose Zen first as the approach to do it. And first of all, there is the paravirtualization interface that allows us to do this very fast. And then what we wanted to explore is also by using the Zen paravirtualization capabilities of running the same approach on top of public clouds. So we actually went ahead and ran this thing on top of GCP. And there is a little trick why we chose GCP to run it is GCP has underneath KVM, and we can do this double paravirtualization there. Turns out that it's very complex in Zen to do a double paravirtualization, essentially having DOM0 have also paravirtualized drivers that allow it to talk down to the infrastructure. So unfortunately, it didn't work in AWS, but it worked in GCP with Zen over KVM. So let's go back and understand a little bit the network access, right? So as I said, what this first part of the work is doing is essentially creating a protocol that allows to paravirtualize socket calls, right? So socket calls are translated into hypercalls. The hypercalls are sent to DOM0. The socket is opened in DOM0. Then any packet, when the data actually is transmitted, the data through a hypercall are moved from the guest down to DOM0, and then DOM0 is responsible for actually running the TCP/IP stack for these packets, and actually sending the packets out. And if you think about it from a security standpoint and an operation standpoint, what this allows us to do also is that all our controls, all our security, all our virtualization, whatever we want to do, for example, in the network, is done completely within DOM0, and the guests, essentially, where the containers are running, are completely unaware of all the operational stuff that we are adding in DOM0 in order to achieve that. Sorry. So the other benefit is that we use only one TCP/IP stack. We don't have a stack at the guest and a stack at the host. We're essentially passing the packets through one TCP/IP stack. And this actually improves performance substantially, and we can concentrate all our forwarding policies, right, within DOM0. But we can do other, even more interesting stuff. For those of you that are familiar with how Docker works, right, Docker uses the idea of namespaces. So it can actually, it puts every container in a namespace, or potentially by doing some of the tricks that Kubernetes is doing with the idea of a pod, you can create a pod, and the pod creates the namespace, whether it's a network namespace or the IPC namespace, and then multiple containers can be launched within the pod, and they actually share a namespace. So the use cases that you have that is that you might have multiple applications that you want to package together as a pod, and then these applications, by sharing the namespaces, some namespaces like network, or storage or IPC, they can feel like they are running together, but they are at the same time isolated. What we can do with the approach that we are describing here is we're essentially combining these operational benefits of pods and namespaces together with virtualization. So what we do is we actually create a namespace for the pod or create a namespace for the container, use all the existing Docker APIs and functions in order to launch this process actually. And then when we actually launch the executable, instead of launching the executable directly to run in Linux, we actually launch the executable in a VM with a very small kernel that works as the system call proxy, and the executable is running essentially as a process within the namespace. So from the perspective of Docker, or for the perspective of an implementation where people are familiar with respect to Docker, this looks and feels like Docker. It looks and feels like it has all the operational benefits of containers. However, the processes are isolated essentially from the underlying operating system through this kernel proxy that is actually proxying the critical system calls. Some other benefits are that there is pretty much zero config for networking inside the VMs, right? There is no need for a bridge potential, even in DOM0. We can move things down. And in reality, it works very easily with the underlying network, right? I don't have to do networking twice. Because when I'm trying to run Docker on top of VMs, on top of a hypervisor, I really end up managing networking twice. In some instances, you will see people running VXLAN in VXLAN, essentially running 2 levels of tunneling in order to achieve what they want. It is very complicated. So what is the first implementation? There is a design document up. Stefano has been trying to get feedback. It is actually a very simple first implementation. It uses one command ring. It's a shared command ring where the guest is going to send the socket calls down to the hypervisor, translate them into the hypercalls. And then it currently actually creates a per socket data ring and event ring. We are looking at ways to optimize this because this can get heavy by essentially creating a shared ring for all sockets within a guest. And the first supported functions are the basic system calls for sockets, socket connect, release, and so on. There is an implementation out there. It is in Git, and we are actively looking for feedback on how to improve the design, how to make it more usable, and potentially find other use cases. I talked to some people that they actually told me that there might be some additional use cases for this type of work in addition to what we are trying to achieve over here. Now, I'm going to show you some benchmarks. We have done some performance analysis also of this to understand what are the performance implications and how it compares with other techniques. And we have used a pretty big machine out in OVH in order to achieve that. And the first performance is, sorry about that, assuming we have an app container, we have a container that is running inside a guest using the technique that I explained, and we have DOM0, and we try to do an hyperf test in order to measure raw throughput between starting from the container, going to DOM0. And the first results that we got are actually this. So this, what it compares is, it compares the net front, net back type of implementation, that is the red line, with the Docker line, that is the orange line, and again with the PV calls line, that is the blue line. And what I mean by the Docker line is we essentially repeated the test assuming that the Docker container talks to the host without any virtualization in order to understand the difference. And what you can see here is that obviously Docker, the direct implementation, has much better performance than everything, right? There is a performance overhead by going through virtualization and I/O even for that. However, there is a significant improvement in terms of raw throughput between the PV call implementation and the net front, net back implementation. We repeated the opposite test, essentially starting from DOM0 and trying to access the container. In this case, what we saw actually is something weird happened, that PV calls had actually much better performance than both Docker and the net front, net back. This is a fluke a little bit. The fact that PV calls had better performance than Docker, right? People would try to understand why. And I'll explain it in the next slide. But essentially, again, PV calls provide substantial performance, right? We managed to reach like 60 gigabits of traffic with something like 4 threads of hyperf running. Now, there is this big gap, right, between PV calls and Docker. It has to do with how Docker does networking. So in the standard deployment that we actually used with Docker, because Docker needs to do NAT everywhere in order to talk between the containers from the outside and so on, they actually chose to have a user process NAT implementation. So for every socket, for every port that they are actually NATing, they actually launch a user socket implementation and a user proxy implementation. And this results in like something like that, where the proxy is consuming something like 200% of the CPU. So that's the reason for this fluke. I think they have an option to disable that, so at this case they will be the same as the PV calls. We also did the benchmark with Apache Bench, right? The question there is to see what is the overhead that the system call, this whole system call open and close is actually putting, and there is an overhead that is introducing. Obviously, if you do very long connections, it's not happening there. We think that the overhead right now, the main reason is because we are creating these dedicated rings for every new socket. So if you are opening new sockets very fast, it creates an overhead. And that's why we are trying to see how we can actually improve the design by creating a shared ring for the data in between all the sockets of a specific guest so that we can improve the system call activation rate. Now, yes? PV.
So that PV call is actually, PV, not VM call or anything, just basically under 64-bit.
Yes, it's a
Syscalls.
yes,
Okay.
yes. So now, if anybody of you is actually using Docker in Mac OS X, you will realize that they are actually emulating what I just described on a much more efficient manner. So this is what you actually use today. So if any of you that have used Docker in Mac OS X, they are doing something like that today. What they are doing is the poor man's approach to that. So essentially, they are actually virtualizing. They use the Beehive hypervisor in Mac OS X. They are having a kernel where they are sending packets, they are converting them to Ethernet packets, they are sending them on Mac OS X, and then they have a proxy there that takes the Ethernet packets and converts them to a new socket call on the underlying operating system. So in this way, they give the illusion in the containers that they are actually opening socket calls on the underlying operating system. That's how Docker for Mac actually works today, right? So this is an approach, but this is obviously a very heavy approach, and it's very slow, right? It's tremendously slow. It's only for a dev environment in your Mac. It's not for production. But this gives you an idea of why other people are needing that. Now, We think that the mechanism is very generic and can be extended for in several other system calls, not just the socket calls. That's where we started. Although you can think of it that on the file system, we can achieve something very similar with 9PFS and the corresponding driver, so we might not need to do it at the system call. However, we can also do a model of co-processing system calls. What I mean by that is that a part of the system call or a part of the admission control, if you want, of the system call is performed at the guest and the rest part is performed at the DOM0. And for anybody, you know, this idea of system call interposition is not new, right? It has been around for a very long time, and there are some specific security risks when you do system call interposition. There is this time of check, time of use type of race condition that essentially somebody gives you a system call, and while you are processing the system call, if the system call refers to a buffer, right, it has a pointer. While you are processing the system call and you're working on the old value of the memory, they go and change the memory, and then by the time the system call is executed underneath, the memory is actually changed, so the actual system call is implemented somewhere else. People have used that as a way to go through and bypass limitations in terms of file system access and so on. So we think we can actually, by doing something like that, we can avoid a lot of these risks. And the other risk is it goes back to a very high performance or very high availability systems, right? That by running different kernel versions between the kernel proxy and DOM0, you get this, again, you get this security by obscurity, or if you want high availability, by the fact that they are not going to have the same bugs, right? So even though the system call is passed through, the two kernels are very likely not to have the same bugs, right? Not guaranteed, but there is a good chance that if a bug was introduced in n+1, it's not there in n, or vice versa. So now I'll show you a little bit of a demo here. The first thing is the performance comparison. So the setup is that we're going to have two containers talking over the Linux kernel, and then we're going to have the same two containers talking over the Syscall proxy and the Paravirtualized interface. So let me start with the straight Docker performance. So what we are doing here is we are logging into this machine in OVH. Stefano was very diligent to make sure that everybody sees that we are running what processor and how much memory we are using, with that it's essentially the same machine that we are using in both cases. And then what we are going to do is we are going to start an iPerf client and an iPerf server as containers, and we are going to do a standard iPerf test. Now, here it's pretty much standard Docker running, no difference at all. Oh, we can even hear the... So here we are starting the iPerf client, and we see that we will get a performance around 12 gigabits per second. That's a single flow iPerf client going between two Docker containers. Okay, now I'm going to go to the corresponding thing using the Paravirtualized system calls. Let me skip through the beginning a little bit. Okay. So we're going to do exactly the same thing here. The only difference is you will see that when we actually start Docker, we are actually starting Docker with a wrapper. And what the wrapper does is it takes the container and runs it inside the virtual machine on top of Zen using this call idea, right? So there are no containers running here, and we run it with a script And you will see what will happen is that there will be a Docker machine that will start here. And sorry, there will be a virtual machine started here. And we are actually now in this machine, and we are actually running the server. And then we do the exact same thing with the client. And that's an interesting thing to show here just a little bit, is that you are seeing that we actually opened on the server port 5001 in order for the server to listen. And you see that this port is actually opened on DOM 0, right? It's actually opened on the hypervisor. It can be seen on the hypervisor as open there. And now we're going to start another Docker container. Same thing, pretty much a standard Debian container. And there is another machine created. And this can be improved. You saw that the machine took maybe a couple of seconds to be created. And we stripped the kernel down. I'm pretty sure it can be stripped more. I think right now it's about 20 megabytes overhead for this kernel. And you see now that, first of all, we are doing iperf directly on 127.0.0.1. And we're actually getting a performance of something like 18 gigabits. That is even better than the direct Docker performance. Now, the second demo that I'm going to show is that we used an old exploit in order to go from a container and download the exploit and actually run it against the kernel. And by doing that, the exploit results in a denial of service attack. Essentially, it crashes the underlying kernel. And then we obviously repeat the same thing here, and the exploit works because we use the exact same kernel. But obviously, what the exploit crashes is the Syscall proxy. It doesn't crash the underlying kernel together with all the other containers there. So there is move it. So we go and download the exploit. This can happen through any mechanism, right, that somebody actually manages to inject an exploit on the Docker container there, right? It can be a Perl web server running somewhere. And we'll run the exploit, and as you would expect, here we are showing the rest of the windows, but as you would expect when you run the exploit, we get a panic in the kernel. And all the containers are actually crashed, right? All the containers and the guests are crashed. It's a null pointer reference there, and then the machine is rebooting, and off we off, right? So we essentially managed to affect a whole bunch of containers here, repeating the same exact attack on the virtualized option, and as you would obviously expect, nothing magic here, but the exploit is going to just crash the guest, and is not going to crash the other containers, right? So it has crashed the guest, but if we go to one of the other windows, you see that the other container is running fine, and if we go on the hypervisor, we can still ping the other container, and so on. So that is a summary of where we are. Stefano, as I said, set up a call to try to discuss in more detail the technical details. Probably I cannot answer all the questions. I can try to answer some of the questions, and we'll be glad to get your feedback. This is where we are trying to move forward and understand what is the community feedback, what are people thinking about it, and see how we can move it forwards. Any questions? Yeah.
So the benefits of a container is basically the density, right?
Excuse me?
The benefits of using a bare metal container is the density, high density.
Yes.
Right? So what is the,
yes. So
memory overhead?
The overhead that we saw here, and that's actually a very good question. The overhead that we saw is we use a minimal kernel, and the kernel overhead is something like 20 megabytes when it starts. That's all the overhead that we see. Intel has done a very good work actually on providing a minimal kernel for running containers. They have done it as part of the clear containers.
Yeah, I think that was something like 24 megabytes.
Yeah.
Yeah.
And so that is the overhead. I don't think memory density, well, memory density is obviously one of the benefits, and there are drawbacks, right? There is this memory drawback, but 20 megabytes or 30 megabytes, right, is not usually a
But
very big
you know, from our experiences, the density significantly gonna be lower if you, for example, use that much memory.
I understand, right? So that's the overhead, right? That's
Yeah.
a well understood overhead, and it's the penalty you would pay for the increased security, right? So it really depends on your environment and your target and applications.
Okay. One more question is, so you kind of modify the system call things because you virtualize system calls. So then you take a risk of breaking as system calls, basically the compatibility. How can you, for example, make sure all system calls are still kind of work as a real Linux or whatever system?
So the idea here is that only a very few number of system calls are actually paravirtualized, right? And they are sent down. The majority of the system calls, the idea is that they will remain the same.
Do you have any number?
I have to get the enum number. Probably all the network system calls that are probably 8 or 9 or 10, whatever is the number. And then maybe another, whatever, I don't know, probably 10, 15, right? So the number is going to be very small if we go do the complete approach, right? We can even start with network and file and solve a lot of the operational and I/O issues and then start extending to the rest. I think it will be the wrong thing to do to try to do a lot of them, because then you lose the benefit, right? So it really has to be minimized to the ones that are affecting operations there.
So about the implementation, can you have 2 or more web servers running in Docker containers on port 80?
Yes. So the way you would do that is the same way Docker does it, right? So you would essentially, put the containers in different namespaces. So nothing, that's what I was trying to explain, nothing prevents you of actually implementing this together with namespaces, right? Because you can create namespaces and instantiate the VMs essentially in different namespaces.
So you create namespaces in DOM0 in that case,
Yes.
in the proxy?
Yes.
Okay. Another question is performance. Do you have any performance data on like connections per second?
Yeah, that's what I was trying to show with the Apache benchmark. Right?
That was...
Essentially, the Apache benchmark was doing very fast connections and was measuring throughput, right? And essentially what we are showing there is obviously if you have connections that are very short-lived.
Okay, because the x-axis had the...
Yeah, I know, right? But
and the y-axis
right.
was
So the
normalized
y-axis was showing throughput, but the implication of this underneath is, right? If you think about the implication underneath is that if you have a lot of very short-lived connections and short-lived calls, you get an overhead. And we know exactly where the overhead is right now. The overhead is in creating essentially a ring buffer for every time a system call is implemented for the data. And that's what we are trying to implement, that essentially improve it by creating a ring buffer for everything. For one ring buffer per guest and multiplexing the data on top of the same ring buffers. And then you obviously don't want one because you have head-of-line blocking, so you want to put multiple ones, and potentially the way you do that is put multiple ones, one per CPU core, so that's how you avoid you spread the load around. So there is work to do to improve the setup time, okay?
Do you think you're going to have to hone each sort of set of system calls or kind of group of system calls so that they perform well? Or do you think you're going to be able to have a generic kind of way of doing things that will work?
I'm hoping that it's going to be a generic way. I don't see why not. But, you know, the devil is in the details, right? But I mean, ideally, we shouldn't need a new protocol for every system call, right? It can become a generic protocol that we can choose, right? Based on whatever configuration filter mechanism, we can choose which system calls to pass under it. There are implications there on the drivers, right? I mean, obviously, the front end, the drivers have to be modified, right? Because the Linux kernel on the guest wants to think that it's doing the whole work, but it's not. Right? So it's not straightforward to take every system call and pass it over there, right? There is work to do. Any other questions?
I have a comment, because you mentioned Stefano's call. I just looked that up on a mailing list. So it's on September the 2nd at 9 a.m. PST or 5 p.m. UK. And there's it's called Technical Call on PV Calls if you want to search Xendivel for it.
Yes.
And then you can engage, with him and the proposal. Any other questions? Oh, and as an aside, as a community, if anyone wants to set up a call or something like that for a specific topic, I'm always willing to set that up. You just drop me a line on lars.kurt@xenproject.org or community.manager@xenproject.org if you can't remember my name.
I have a question about the interfaces that you guys are using. Is this, so you said earlier that we're assuming that it's the same operating system for the host and the guests, right?
Same type of operating system.
Okay, so it would all be Linux
Yes.
in this example.
Yes.
So your PV interfaces, they're ABI compatible as well?
Yes.
Okay.
So actually, it is the way I think Stefano has been doing it is essentially paravirtualizing the POSIX call. But I would ask you to send a note to Stefano and get the details. I'm probably not the best person to answer exactly this question.
Okay. Yeah, I think you can avoid having to recompile if you.
Yeah. No, there is no recompilation. Yeah.
Cool. Okay. Thank you.
Thank you, guys.